quasiparticle scattering. This is an important measurement technique used for looking at helium-3, superfluid helium-3. Notice how this pointer works.
A bit different
No
one.
one knows how it works. We will be just.
So from here.
Yeah.
Okay. First of all, I would like to say thank you to organizers for inviting and giving the opportunity to make this talk. The talk is interpretation of quasiparticle scattering measurements in superfluid helium-3b, and this work was done in collaboration with Professor Karl Barenghi, Professor Yuri Sergeyev, and also Dr. From Newcastle University, and also Dr. Andrew Bagley from University of Glasgow. And this work is directly linked to the experiments conducted in University of Lancaster by the Professor George Pickett's group in order to study quantum turbulence in helium-3b using the Andreev reflection technique. Let me introduce some background information about the physics, the experimental measurements, and our numerical calculations and theoretical estimations are based on. The superfluid helium-3b is a Fermi liquid, and since the temperature is no longer zero, there exist the excitations. Excitations are formed by the quasiparticles above the Fermi surface and by the empty places or quasi-holes below the Fermi surface. The corresponding spectrum is given by this expression, which refers to the kinetic energy of the quasiparticle with momentum p counted from the Fermi energy. And it may be either positive for quasiparticles or negative for quasi-holes. The superfluid helium-3 B phase is described by the two-fluid model. It means that there is a normal, alongside the superfluid component, there is a normal fluid component as well, and the superfluid component is formed by the pairing of quasiparticles into the Cooper pairs, which introduce some kind of energy scale appeared in the order parameter, and it's called gap parameter, and also in the space introduce spatial case scale, which is called coherence length, and it refers to the size of the Cooper pairs. The most important is that in difference from the A phase, B phase is characterized by the well-defined pace, and well-defined pace and superfluid velocity of any superflow excited in the system is proportional to the gradient of the phase and it means that superfluid fraction is inherently irrotational, and rotation may be and the superfluid fraction can be involved in the rotational motion only by injecting the quantized vortices into the system. Quantized vortices on the qualitative level characterized by same properties as quantized vortices in the superfluid helium-4 or in any superfluid Bose system. And what is most important, differences are appearing only on the quantitative level because the numbers are different. And what is most important, again, the velocity field in B phase induced by the vortex filament of arbitrary arbitrary cured vortex filament, again described by the Biot-Savart law. Here S point are points on the vortex line. So the normal fraction consists with the thermal excitations, and in superfluid phase the excitation spectrum is changed. It is expressed by the so-called Bogolubov-Cooper-Schrieffer spectrum. And now we can speak about the particle-like excitations with EP positive and hole-like excitations with EP negative. In any superflow, this spectrum becomes shifted, and here appears the additional term. We are interested. This term describes actually the interaction between the excitations and velocity field excited in the superfluid part. But we are interesting. Our interest is concerned with the velocity field excited by the quantized vortices. Since quantized velocity field excited by quantized vortices is inhomogeneous, excitation moving along the superfluid gradient may experience either effective potential energy barrier or potential well. We are dealing with very low temperatures, and we are at the vicinity, in the vicinity of the 0 bar pressure. And at such conditions in superfluid helium-3b, some specific conditions are introduced. First condition is that quasiparticle gas is extremely rarefied, so it gives it enables us to exclude the interparticle collisions, which described quantum mechanically. Secondly, we can also consider the gap parameter almost constant, and also there is another condition which appears in the theory, that the interaction terms varies on the scales, on the spatial scales, much larger than coherence length, and it gives the possibility to describe the excitations as a compact objects of the momentum and position. And we can consider the excitation spectrum as a Hamiltonian, and describe the dynamic of this quantum system using the classical mechanical methods. It is a corresponding Hamiltonian equations describing the dynamics of the excitation in the velocity field excited, induced by the quantized vortex. And it is an example of the single rectilinear vortex. This is a velocity field excited by this such vortex, and it is effective potential felt by the quasiparticle or by the excitation propagating in this field. And you can see that one side is an effective potential barrier, while another side is an effective potential well. This side is partly reflected and reflective, and this side is absolutely transparent for the excitation, for the quasiparticles. The interaction of quasiparticles and the velocity between the quasiparticles and velocity field of vortices characterized by the very specific properties, because it it is a reflection, but this reflection is not an ordinary reflection. It's an Andreev reflection, which characterized by the branch conversion. So during the reflection, excitation change its flavor. If, for example, we have incident quasiparticle, the reflected object is a quasi-hole. Also, the reflection happens, it's a retroreflection. It's a reflection happens it's an absolute back reflection, and reflected excitation retraces the path covered by the incident excitation from the beginning to the target, and Also, interaction undergoes almost without exchange of momentum. There is no any pressure exerted from the quasi-particle system to the quantized vortex system. Only case which can be solved analytically is a case of single vortex, because this system characterized by the integrals of motions. It has 3 integrals of motions, and in 3-dimensional case, and it has 2 integrals of motions in 2-dimensional case. We solved this and found the thermal reflectivity of the single vortex, and thermal reflectivity of the single vortex, and generalize this results on the system of the straight vortices, and found the reflectivity. It is reflectivity as a function of the line density, and it is expressed by this equation. Alpha is a small parameter, and for the reasonable line densities, the alpha L, the exponent, is a small dimensional parameter, and gives the ability to linearize this equation. So the reflection coefficient of the linear vortex system is a linear function of the line density. But it is an idealized case, I should say this. And other cases are not solved analytically, so we need to rely only on numerical calculations, and we have done it. We numerically simulate this set of equations, first to describe the quasiparticle dynamics. This second pair describes the vortex dynamics. We use the vortex filament method. Actually, Andrew was working on this problem, and performed the full BSLR simulations. And what we are measuring the total incident energy of total energy of the incident flux, counting and the energy of the reflected flux, and their relation actually defines the thermal reflectance of the system. We study the turbulent tangles of different line densities in this range, and in every time the turbulent system was satisfying the Kolmogorov spectrum -5/3 law. We also characterize the tangles. We find the probability density function of the curvatures of these tangles, and what was more surprising for us, the mean values of the curvatures lie in the very short interval. They're almost same, even for such a big difference between the line densities. It lies 47 plus minus 1 centimeter minus 1. So whole so results we are obtaining are the coming only from the line densities, and it is a main result depicted on this picture. For the reasonably low line densities, we have almost linear behavior. Then we have some kind of plateau. We called it near saturation region, and the origin of this saturation is a geometrical screening. We also study the rectilinear vortex systems and compare it to the idealized estimation which were performed by us and which also used by Lancasterian people, and found quite a dramatic difference between the calculations, numerical calculations, and analytical estimations. And it is a these two lines are exhibit the reflectance, thermal reflectance of the turbulent tangles with mean curvature of 47 centimeter and with system of the regular vortex rings with almost same curvature, and you can see that even they are different. They are different. They are not identical systems. They are producing velocity field with almost same intensity. Okay. Okay. In summary, is that we also probe the ring system with higher, so with higher curvature, and find that curvature also reduces the reflectance, thermal reflectance of it. Is a main conclusion of my talk, and thank you very much for attention.
Questions? We'll meet again in about half an hour.